This is SpaceTime Series 24, Episode 138, for broadcast on the 3rd of December 2021. Coming up on SpaceTime, a new study says 1 in 5 galaxies could be hidden, hundreds of new planets discovered by NASA, and Russia launches a new module for the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers at the University of Copenhagen's Cosmic Dawn Center have discovered two previously invisible galaxies 29 billion light-years away. The discovery suggests that up to 1 in 5 such galaxies remain hidden from our telescopes, camouflaged by cosmic dust. The light from the two galaxies, which have been named Rebels 12-2 and Rebels 29-2, has travelled about 13 billion years to reach the Earth. But when you include the expansion of the universe in those calculations, it means those galaxies are now located some 29 billion light-years away. The discovery, reported in the journal Nature, changes science's perception of the universe's evolution since the Big Bang. That's because the new discovery suggested the very early universe must have contained many more galaxies than previously thought. The two newly discovered galaxies had been invisible in optical light because they're hidden behind a thick layer of cosmic dust that surrounds them. But ALMA, the Atacama Large Millimeter Submillimeter Array telescope in Chile's Atacama Desert, was able to detect them using radio waves. This is SpaceTime. Still to come, hundreds of new planets discovered by NASA, and Black Sky launches its rocket from southern Queensland. All that and more still to come on SpaceTime. NASA has announced the discovery of another 301 extrasolar or exoplanets, that is, planets orbiting stars other than the Sun. The new discoveries bring the total number of confirmed extrasolar planets to 4,569 since the discovery of the first back in the mid-1990s. The new discoveries were made using new deep neural supercomputer networks that are better at distinguishing real exoplanets from false positives. Deep neural networks are machine learning methods that automatically learn a task when provided with enough data. This particular NASA neural network, called ExoMiner, supplements people who normally comb through piles of data, deciphering information, looking for possible exoplanets. The program sifted through data gathered by NASA's Kepler Space Telescope and during the follow-up K2 mission. Kepler focused on just one small part of the sky, looking for any changes in brightness to any of the hundreds of thousands of stars in its field of view. That change in brightness could have been caused by a planet transiting in front of the star as seen by Kepler. The key is working out which are transiting planets, causing the star's light to dip, and which are simply random occurrences, causing false positives. This is SpaceTime. Still to come, Black Sky launches from southern Queensland, and Russia launches a new module to the International Space Station. All that and more still to come on SpaceTime. Black Sky Aerospace has successfully launched a satellite security test payload from its Goondiwindi launch complex in southwestern Queensland. The suborbital flight for cybersecurity company Bitscore tested new software and follows similar tests aboard the International Space Station. The software will help providers upgrade onboard satellite cybersecurity as they join the 5G network. The new tests were designed to see how well they performed under the rigours of a rocket launch, reaching 30,000 feet in Mach 2 in just 10 seconds. 3 more similar test launches are planned. In 2018, Black Sky's solid fuel-powered Saturn 190 sounding rocket carried a number of experimental payloads on a short suborbital flight. The company then began manufacturing solid fuel rocket motors for use in boosters in 2019. This is SpaceTime. Still to come, Russia launches a new module to the International Space Station, and the December solstice, the Edda Carina ticking time bomb, and the annual Geminids meteor shower are among the highlights of December on Skywatch. A Russian Soyuz rocket has blasted off carrying the new Prichal docking module for the International Space Station. The launch was carried out from the Baikonur cosmodrome in the Central Asian Republic of Kazakhstan. Prichal, which means pier in Russian, is the second new addition to the Russian segment of the orbiting outpost this year. It follows the arrival of the troublesome Nilka science module earlier this year. Nilka took a stunning 25 years to build, and then suffered computer software issues once docked to the space station. They caused it to suddenly fire its thrusters, sending the orbiting outpost out of control. The new 5-ton Prichal is designed to dock up to 5 spacecraft at a time. The module was packed with cargo for the journey to the space station, including food, repair equipment, and hygiene supplies. Meanwhile, in an attempt to take attention away from their recent anti-satellite missile test, Moscow's pointed out that mission managers have just been forced to maneuver the International Space Station out of the way of a piece of debris from a Chinese weather satellite destroyed in an earlier Chinese anti-satellite missile test. The orbiting outpost was raised some 1.2 kilometers to avoid colliding with space junk from the Fenyang 1C weather satellite, which was deliberately blown up by Beijing back in 2007. Moscow's been widely condemned for last week's test, which saw a Russian missile deliberately blow up a disused Soviet Union-era spy satellite, leaving a massive debris cloud which will threaten space navigation for decades to come. This is SpaceTime. And time now to turn our eyes to the skies with December Skywatch. December is the 12th and final month of the year in both the Julian and Gregorian calendars. December got its name from the Latin word decim, meaning 10. That's because it was originally the 10th month of the year in the old Roman calendar, which began in March. The astronomical highlight of the month is the December solstice, which this year occurs at 2:59 a.m. Australian Eastern Daylight Time on the morning of Wednesday, December the 22nd. That's 10:59 a.m. on Tuesday, the 21st of December, US Eastern Standard Time, and 15:59 on the afternoon of Tuesday, December the 21st, Greenwich Mean Time. This is when the Sun appears to reach zenith directly above the Tropic of Capricorn. In the United States and most of the Northern Hemisphere, it marks the winter solstice, signifying the first day of winter. But the good news is that from now on the days start to get longer again. South of the equator, summer has well and truly arrived, and the days are usually at their warmest. The seasons occur because of the tilt of Earth's spin axis, which is inclined at 23.4 degrees in relation to the Sun. Generally speaking, Earth's axis always points to the same position in space, regardless of the position of Earth in its orbit around the Sun. So on the day of the December solstice, Earth's south pole is tilted towards the Sun, so the southern hemisphere gets more daylight and more direct sunlight, and so it's hotter and the southern hemisphere is in summer. 6 months later, during the June solstice, the north pole is tilted towards the Sun, and so it's the northern hemisphere which experiences summer, while the southern hemisphere gets less daylight, longer nights, and the sunlight strikes the Earth at a more shallow angle, meaning less heat, and the southern hemisphere's in winter. Of course, between these two, we have the March and September equinoxes, when the northern and southern hemisphere get roughly equal amounts of daylight and heat, giving us the seasons of spring and autumn. Now, earlier we said that, generally speaking, Earth's axis always points to the same position in space, regardless of Earth's orbital position around the Sun. And while that's true in our day-to-day lives, Over geologic time, a gravity-induced effect known as axial precession causes a slow and continuous change in the orientation of the Earth's rotational axis. You can see the same effect in the precession of a spinning top as it revolves around its axis, and the tilt of its axis slowly traces out a circle. Earth's precession is known as the precession of the equinoxes, because the equinoxes moved westwards along the ecliptic relative to fixed background stars. This slow precession means that over a period of 25,772 years, the position of the south and north celestial poles appears to move in circles against the space-fixed backdrop of stars. So while today the star Polaris lies approximately at the north celestial pole, this will change over time, with Gamma Cephei becoming the North Star in around 3,200 years' time. It also means that the seasons would slowly change to different calendar months, but we make adjustments for that in the calendar to compensate. In most parts of the world, the seasons begin on the day of the solstice or equinox. However, Australia follows meteorological seasons, which begin on the first day of a particular calendar month. So it's the first day of December for summer, the 1st of March for autumn, the 1st of June for winter, and September the 1st for spring. Now, it's also worth mentioning now that because of the relatively small elongation in Earth's orbit around the Sun, Earth's seasons are determined by its axial tilt rather than its orbital distance from the Sun. Currently, Earth's closest orbital position to the Sun, known as perihelion, occurs about 2 weeks after the December solstice, and its furthest orbital position from the Sun, aphelion, will occur about 2 weeks after the June solstice. This means the next perihelion will occur on Tuesday, January the 4th at 17:52 in the afternoon, Australian Eastern Daylight Time, when the Earth will be 147,105,052 kilometres from the Sun. That'll be at 1:52 a.m. US Eastern Standard Time and 6:52 in the morning, Greenwich Mean Time. Like axial precession, the Earth's orbit also changes gradually over geologic time, getting more or less elongated and changing perihelion and aphelion. Even the degree of the tilt of Earth's axis changes over thousands of years. Now, collectively, these are all referred to as Milankovitch cycles, after the Serbian geophysicist Milutin Milankovitch, who in the 1920s hypothesized that variations in eccentricity resulted in cyclic variation in the solar radiation reaching the Earth, and that this strongly influenced Earth's climatic patterns. And no, despite what the climate change deniers claim, you can't use that as an excuse for global warming. Okay, let's start our tour of the night skies in the west, where midway up from the horizon, you'll find Fomalhaut, the brightest star in the constellation Pisces Austrinus, the southern fish. Fomalhaut is a young white spectral type A main sequence star, about 1.8 times the diameter of the Sun, and located some 25 light-years away. A light-year is about 10 trillion kilometres, the distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Main sequence stars are those undergoing hydrogen fusion into helium in their core. Astronomers describe stars in terms of spectral types, a classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, then spectral type G yellow stars. That's where our Sun fits in. Spectral type K orange stars, and the coolest and least massive stars are referred to as spectral type M red stars. Now, each spectral classification can further be subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and then a Roman numeral to represent luminosity. So, putting all that together, our Sun becomes a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were born as spectral type M red dwarf stars but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a category between the largest planets, which can be about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. In 2008, astronomers detected planets orbiting around Fomalhaut. It's not known if anyone was looking back. 5,000 years ago, the ancient Mesopotamians used Fomalhaut to mark the Northern Hemisphere's winter solstice. Now, turning to the left of Fomalhaut is Achernar, or Alpha Eridani, the brightest star in the constellation of Eridanus the River. Located 139 light-years away, Achernar has about 7 times the diameter of the Sun and rotates some 15 times faster, giving it a distinctly oblate shape. See, what happens is the rapid rotation flattens the star's top and bottom and bulges out its middle. In fact, the star's equatorial diameter is some 50% greater than its polar diameter. Achernar is actually part of a multiple star system, Alpha Eridani A and Alpha Eridani B. The primary star, Alpha Eridani A, is a hot blue spectral type B main sequence star. Its smaller companion, Alpha Eridani B, is a spectral type A white star. The pair orbit each other at a distance of about 12 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. Moving further left from Achernar and just above the horizon is the star Canopus. It's the brightest star in the southern constellation of Carina the Keel and the second brightest star in the night sky after Sirius. Canopus is a white giant, nearing the end of its life. It's located about 310 light-years away. It has about 8.5 times the mass of the Sun, but has expanded out to some 71 times the Sun's diameter. Canopus has some 1,300 times the brightness of the Sun, and is in fact the brightest star within 700 light-years of Earth. Its name originates in Greek mythology from the time of the Trojan Wars, and the navigator for Menelaus, the king of Sparta. Located between Canopus and the Southern Cross in Carina is the Trumpler-16 open star cluster, and within it is the ticking time bomb known as Eta Carina. Eta Carina is a pair of huge blue stars undergoing the final violent phase of their existence before exploding as massive core collapse supernovae. The binary system, located some 7,500 light-years away, is buried deep inside the giant Carina Nebula, a massive cloud of gas and dust stretching from 6,500 to 10,000 light-years away. The stars in Eta Carina are classified as highly luminous spectral type O blue hypergiants. The primary stars are estimated to be somewhere between 150 and 250 times the mass of the Sun, with some 5 million times the Sun's luminosity, 800 times its radius, and a surface temperature of up to 32,500 Kelvin. It's also the only known star to produce ultraviolet laser emissions. As the star counts down to its ultimate fate, it's already lost about 30 times the Sun's mass. The companion star, although smaller than the primary at just 30 to 80 solar masses and 20 times the Sun's radius, is even hotter, with surface temperatures of 37,200 Kelvin. The two stars orbit each other every 5.54 Earth years, cocooned in a thick twin-lobed cloud of gas and dust known as the Homunculus Nebula. This bipolar emission and reflection nebula was created when Eta Carina underwent a spectacular eruption beginning in 1837. Known as the Great Eruption, it eventually reached its peak in 1843, by which time it was one of the brightest objects in the night sky, almost as bright as Sirius, before gradually fading away again by 1856. Eta Carina underwent a slightly smaller eruption in 1892, and it has again been steadily brightening since around 1940. Eta Carina and its surrounding cloud of gas and dust generate huge amounts of infrared radiation, making it the brightest infrared source in the sky. With both stars nearing the end of their lives on the main sequence, they're expected to go supernova in an astronomically short period of time. When it does go supernova, Eta Carina will be easily visible from Earth in daylight, and may even become brighter than the Moon for months on end. No one knows exactly when Eta Carina will go supernova, but it's fair to say it'll be any day now. That could mean tomorrow, or it could mean in 1,000,000 years from now. Now, a single star, originally around 150 times the mass of the Sun, would typically reach core collapse as a Wolf-Rayet star within, say, 3 million years. At low metallicity, many massive stars will collapse directly into a black hole with no visible explosion or a subluminous supernova, and a small fraction will produce a pair instability supernova. But at solar metallicity and above, there's expected to be sufficient mass loss before collapse to allow a visible supernova to occur. If there is still a large amount of expelled material close to the star, the shock formed by the supernova explosion impacting the circumstellar material can efficiently convert kinetic energy into radiation, resulting in a superluminous supernova or even a hypernova, several times more luminous than a typical core collapse supernova and much longer lasting. And highly massive progenitors may even eject sufficient nickel to cause a superluminous supernova simply from radioactive decay alone. Now, the resulting remnant would be a black hole, since it's highly unlikely that such a massive star could ever lose enough mass from its core not to exceed the limit for a neutron star. But the fact that Eta Carina also has a massive companion star brings a lot of other possibilities into consideration. For example, if Eta Carina A was rapidly stripped of its outer layers, it might be a less massive WC or even WO-type star when core collapse was reached. And this would result in a Type 1b or Type 1c supernova, due to the lack of hydrogen and possibly also helium. And that would be interesting because these supernovae are thought to be the progenitors of some types of gamma-ray bursts. Gamma-ray bursts represent the most powerful explosions in the universe since the Big Bang. Now, one theory for Eta Carina's ultimate fate involves it collapsing down to form a stellar mass black hole with the energy released as jets along its axis of rotation as a gamma-ray burst. Now, a typical core collapse supernova at the distance of Eta Carina would look as bright as Venus, the third brightest object in the sky after the Sun and Moon. But a superluminous supernova could be 5 magnitudes brighter, potentially the brightest supernova in recorded history. Now, Eta Carina is not expected to produce a gamma-ray burst, and its axis is not currently aimed near Earth. At 7,500 light-years distant, it's not expected to directly affect terrestrial life on Earth thanks to our planet's atmosphere and magnetosphere. But still, Earth's ozone layer could be damaged, as would any orbiting spacecraft and any astronauts in space at the time. At least one scientific paper has projected that a complete loss of Earth's ozone layer is a plausible consequence of an Eta Carina supernova. And of course, that would result in a significant increase in the amount of ultraviolet radiation reaching the Earth's surface from the Sun. But realistically, this would require a typical supernova to be closer than 50 light-years to the Earth. And even a potential hypernova would really need to be closer than Eta Carina is. Okay, let's turn to the east now, and looking just above the horizon is the star that outshines Canopus to take the title as the brightest star in our night sky. It is, of course, Sirius the Dog Star, and next to it in the northeastern skies just above the horizon in the constellation Orion the Hunter, you'll see the very bright red star, the red supergiant Betelgeuse, better known to most people these days as Betelgeuse. Don't say it 3 times. It doesn't really matter what you call it because its name has been corrupted and changed over time. In ancient times, before centuries of mispronunciation, the name started out as Iptaliausa. Betelgeuse is one of the largest and most luminous stars visible with the unaided eye. Located some 430 light-years away, this bloated old red giant is nearing the end of its life. It's truly massive, some 1,100 times the diameter of the Sun, and nearly 100,000 times as bright. Like Eta Carina, Betelgeuse is destined to explode as a core collapse supernova sometime in the near future. Betelgeuse marks the right shoulder of Orion the Hunter, although of course it's upside down from the perspective of anyone in the southern hemisphere, as Orion was a hunter in Greek mythology, and so the constellation was viewed from the northern hemisphere. The earliest depiction that has been linked to the constellation of Orion is a prehistoric mammoth ivory carving found in a cave in the Arch Valley in West Germany in 1979. Archaeologists estimate that it was fashioned between 32,000 and 38,000 years ago. The distinctive pattern of Orion has been recognized in numerous cultures around the world, including the ancient Babylonian star catalogues dating back to the Late Bronze Age. In Greek mythology, Orion became a gigantic, supernaturally strong hunter of ancient times. He was the son of a Gorgon and Poseidon, also known as Neptune, the god of the sea, in Greco-Roman tradition. The goddess Sky became angry with Orion after he boasted that he would kill every animal on Earth. So she sent a scorpion to sting Orion to death. However, Ophiuchus the serpent-bearer revived Orion with an antidote, and this is given as the reason why the constellation Scorpius chases Orion across the sky, with the constellation Ophiuchus standing midway between them. The other major stars in Orion are Rigel, Orion's left foot, blue hypergiant. Having exhausted its hydrogen fuel supply in its core, Rigel is now swollen out to between 79 and 115 times the Sun's radius. It's now fusing heavier elements in its core, meaning it too will soon likely supernova and collapse to form a neutron star. Rigel is estimated to be anywhere between 120,000 and 279,000 times as luminous as the Sun. It's actually a binary system located 860 light-years away. Its companion star Rigel B is some 500 times fainter than the supergiant Rigel A, and visible only through a telescope. Rigel B is itself a spectroscopic binary system comprising two main sequence blue-white stars. Spectroscopic binaries are double-star systems orbiting each other in such a way that they can only be visually separated from our vantage point here on Earth by their separate spectroscopic signatures. The two stars making up Rigel B are estimated to be 3.9 and 2.9 times the mass of the Sun respectively, and one of these stars, Rigel BB, may itself be a binary. Rigel B also appears to have a very close visual companion, Rigel C, of almost identical appearance. The third brightest star in Orion is Bellatrix, Orion's left shoulder. It's a spectrotype B main sequence blue star with about 8.6 times the mass and 6 times the radius of the Sun. Bellatrix is about 250 light-years away. It has an estimated age of 25 million years. That's old enough for a star of this mass to have consumed most if not all of the hydrogen in its core and begin to evolve away from the main sequence into a blue giant. Now, if you look at the three stars which make up Orion's belt, you'll see another three stars which make up Orion's sword hanging from the belt, and again, that's hanging upwards for those of us in the southern hemisphere. If you look carefully at the middle star, you'll notice it's a little fuzzy looking. That's because it's not a star, but the great nebula of Orion, Messier 42. Located just 1,344 light-years away, M42 is the nearest massive star-forming region to the Earth. The nebula is estimated to be some 24 light-years across, with a mass of over 2,000 times that of the Sun. The Orion Nebula is one of the most scrutinized and photographed objects in the night sky, and is among the most intensely studied celestial features. The nebula has revealed much about the process of how stars and planetary systems are formed from collapsing molecular clouds of gas and dust. By studying M42, astronomers have directly observed protoplanetary disks, brown dwarfs, intense and turbulent motions of gas, and the photoionizing effects of massive nearby stars in the nebula. The Orion Nebula also contains a very young open star cluster known as the trapezium due to its asterism of 4 primary stars. The trapezium is a component of the much larger Orion Nebula cluster, an association of some 2,800 stars within a diameter of just 20 light-years. One of the most stunning nebulae in the constellation Orion is the spectacular Horsehead Nebula Barnard 33. The Horsehead is a dark nebula located just south of the star Alnitak, which is the furthest east on Orion's belt and is part of the much larger Orion Molecular Cloud Complex. Located around 1,500 light-years away, the Horsehead Nebula was first recorded in 1888. It's one of the most identifiable nebula because of the shape of its swirling cloud of gas and dust, which really does bear a striking resemblance to a horse's head when viewed from Earth. One of the big highlights of December is the annual Geminids meteor shower, which usually peaks around December the 13th and 14th. Radiating out from the direction of the constellation Gemini, the Geminids are unusual in that they're not generated by a comet as most other meteor showers are, but they're produced by the debris trail left behind by the asteroid 3200 Phaeton. This makes the Geminids, together with the Quadrantids, the only major meteor showers not originating from a comet. 3200 Phaeton is highly unusual. Its high orbital eccentricity more closely resembles that of a comet than an asteroid. And it may in fact be an asteroid that's simply run out of the volatile gases that characterize a comet. Phaeton's orbit crosses all the inner terrestrial planets, Mercury, Venus, Earth and Mars. It occasionally comes within 10 million kilometers of Earth. But its closest approach will be on December the 14th, 2093, when it will pass just 2,960,000 kilometers from Earth. Phaeton's roughly 5 kilometers wide and is classified as potentially hazardous, which is interesting because it was named after the son of the Greek sun god Helios. Legend has it that Phaeton almost destroyed the Earth by stealing Helios' chariot and scorching the Earth with the sun, almost causing the apocalypse. But isn't that typical of a boy borrowing his dad's car without permission? Anyway, Phaeton approaches the Sun closer than any other named asteroid, with a perihelion of less than 21 million kilometers. That's less than half of Mercury's perihelion distance. And coming so close to the Sun causes Phaeton's surface temperature to reach over 750 degrees Celsius. Observations by NASA's Stereo spacecraft have observed dust trails radiating off its surface. And in 2010, Phaeton was detected actually ejecting dust. Scientists think intense heat generated by its close approaches to the Sun causes fractures in gravel and rocks on the asteroid's surface, similar to mud cracks in a dry lake bed. Phaeton's composition also fits the notion of a cometary origin. It's classified as a Type B asteroid because it's composed of dark material. Type B asteroids are thought to be primitive, volatile-rich remnants of the early solar system. Its composition, orbit and dust trail have led astronomers to refer to Phaeton as a rock comet. The Geminids meteor showers it produces have a yellowish hue, and they tend to be a bit larger and more solid than typical meteors from comets. They also move more slowly, travelling at around 35 kilometers per second, compared to some cometary meteor showers, which can travel at speeds of up to 72 kilometers a second. The Geminids are thought to be intensifying every year, with recent showers seeing up to 160 meteors an hour under optimal conditions. In the Northern Hemisphere, expect to see up to 120 meteors per hour between midnight and 4 a.m., but only in dark skies. Well north of the equator, the radiant rises about sunset, reaching a usable elevation from local evening hours onwards. But in the Southern Hemisphere, you won't see too many meteors, perhaps 10 to 20 an hour. That's because the radiant doesn't rise above the horizon. Now, for our listeners in the Northern Hemisphere, there's a second meteor shower in December, the Ursiids, radiating out from Ursa Minor, the Little Dipper. The Ursiids are generated by debris left behind by the comet 8P Tuttle. They're a compact stream peaking on the night of December 22nd and the early morning hours of December the 23rd. Just look towards the bowl of the Little Dipper and you might see maybe 10 meteors an hour. And now, with the rest of the December night skies, we're joined by Jonathan Nally, editor of Australian Sky and Telescope magazine.
G'day, Stuart. Well, December, let's start with the eastern part of the sky. If you go out in the middle part of the evening, 8 o'clock, 9 o'clock or something this time of year, about halfway up from the horizon, you're going to see our favourite constellations, your favourite constellation, my favourite constellation. It's Orion the Hunter. It's lots of people's favourite constellation because it just looks amazing. It's got the three middle stars that forms the Hunter's Belt. You've got Rigel and Betelgeuse, the two big stars at either end. If you've got good dark skies, you can actually see the Orion Nebula just with like using what's called averted vision. You don't look directly at it. You just look out the side of your eye. You can just see this little smudge of light, and that's the Orion Nebula. Get some binoculars onto it even. It'll look even better. And, of course, through a telescope, it looks pretty spectacular. But Orion is just the best. A little bit to the west of Orion, you'll see a reddish star that makes up one corner of a triangle or wedge of stars. You can't really miss this wedge of stars. The star is called Aldebaran, and the triangle is a star cluster called the Hyades. Now, the Hyades is what astronomers call an open star cluster, where the stars are only sort of loosely gravitationally bound to each other, because there's another kind of star cluster they call a globular star cluster, where there are so many of these stars, and they're all packed in so tightly that it forms like a ball, a huge ball, of course, out in space, but a sort of a round shape, whereas the Hyades is an open star cluster. It's about 153 light years away, which might sound a lot, but that's actually really more or less next door in space terms. So the Hyades is one of the closest open star clusters that we can see, and that's really why you can see it, because it's so close. So get out and have a look at that one if you can. Now, there's another smaller but even prettier star cluster a little bit further around to the west, around to the left from the Hyades, and this is the Pleiades, also known as the Seven Sisters. So called because when stargazing from dark skies, most people can make out 7 stars in this cluster just with the unaided eye. I've heard of people making out 12 or 14 or so. Some people might only see 5 or 6. All depends on your eyesight and how dark the sky is and whether you've given your eyes time to adjust and all that sort of thing. But it looks really, really pretty, a very compact little star cluster. But if you get a pair of binoculars onto it, it looks really good because then you can pick up fainter and fainter stars that are members of this star cluster. The cluster itself has about 1,000 stars, but most of them are so faint, of course, that you can't see them with the unaided eye. You do need a telescope. Now, in Japan, the Pleiades star cluster is known as Subaru. And if you take a look at the badge on the front of any Subaru car, you'll see that the Subaru badge is actually a little group of stars in the shape of this star cluster. So amaze your friends with that fact. That's pretty incredible, isn't it? Now, let's head down to the far southern skies, when at this time of the year you've got the Southern Cross upside down. So middle of the evening, the Southern Cross is upside down. Now, depending on your latitude, it's either right on the horizon for someone viewing from the latitude of, say, Sydney, or it's just above the horizon for those at more southerly latitudes, if you're in Melbourne or Adelaide, Perth, Tasmania, or equivalent latitudes in South America or Southern Africa. But if you're further north than the latitude of roughly Sydney, then you're not going to see the cross at all because it's down below the horizon, not visible until the early morning hours when the Earth has turned a bit on its axis and the cross is sort of now poking its head above the horizon. If you've got good dark skies, what you can see very easily down in the south, in fact quite high up in the sky down in the south, are the 2 nearest sizable galaxies to our own, with the large and the small Magellanic Clouds, named after Magellan. Now, these are, as I say, situated really nice and high directly to the south this time of the year, in the middle evening. They just look like faint, fuzzy clouds, but they are, in fact, galaxies full of millions of stars. Speaking of stars, just to the east of the large Magellanic Cloud is the star Canopus, which is the second brightest star in the night sky. And further still around to the east, you've got the star Sirius, which is the brightest star in the night sky. It's also known as the Dog Star because it's in the constellation of Canis Major, or the Greater Dog. Now, it's interesting to compare these 2 stars. You've got Sirius, which seems much brighter, but that's because it's closer. It's only about 9 light years away. Canopus is 310 light years away, but it is intrinsically much brighter. It just looks a bit dimmer than Sirius because it's so much further away. Canopus, in fact, is 8 times more massive than our Sun, whereas Sirius is only about twice the mass of our Sun. So when you look up and you see stars, you see the different brightnesses, it's not necessarily an indication of how intrinsically bright that star is. You've also got to take the distance into account. So there are any number of examples of stars that are close and therefore appear bright, whereas ones that are really much brighter are further away and therefore look dimmer. You can also get the sort of the opposite effect too. You get some stars that are very intrinsically bright and are close, and other stars that are dim or also close, look about the same brightness or magnitude, as astronomers call it. Now let's take a look at the planets and see which ones we can see at the moment. Well, Mercury is pretty hard to see this month. Up until around the middle of December, it's lost in the glare of the sun after sunset. But after that, as each day goes by, it slowly begins to rise above the western horizon towards the end of the month, but very low. So you're going to have a hard time spotting it, really, unless you have a very clear horizon, no hills or buildings or trees and things in the way. Much easier to spot will be Venus and Saturn and Jupiter, all of them in a line in the western sky after sunset. They'll be sort of one above the other. And all 3 are going to drop lower and lower toward the horizon as the days go past. So make sure you get out and have a look at them now, because they're all going to disappear from view over the next month and a half, 2 months or so. Now, Venus is the one in the bottom, you've got Saturn in the middle, and you've got Jupiter above. You really won't be able to miss them. Venus is really bright, Jupiter's really bright, and Saturn's not quite so bright, but it's in the middle between these 2, so it's pretty easy to spot. You can't see anything much through a telescope with Venus, but if you do have access to a telescope, take a look at Saturn's rings and the cloud bands and the moons of Jupiter, because even a small telescope will show those quite nicely. Finally, we've got Mars. Mars is in the morning sky, very low on the horizon, in the dawn glare just before sunrise. I should say dawn twilight, put it that way, just before sunrise. and it's going to rise a little higher as each day passes through the month. Now, the big thing to look for is not this month, but the 1st of January 2022, when the moon is going to move in front of Mars, as seen from our vantage point here on Earth. That's what astronomers call an occultation, coming from occult, which just means to make dark, or make invisible. So, the moon's going to move in front of Mars on January the 1st, but not everyone's going to see it, unfortunately. You have to be in the right spot, a bit like a solar eclipse, I guess. So for those in Australia, only those people in the sort of southeastern part of the corner of the continent will be in the right place. You're talking Canberra, Melbourne, Adelaide, and places in between. Everyone else, though, will see the moon almost move in front of Mars. It'll be like a near miss. Mars will just miss the edge of the moon. So whether you get to see the moon cover up Mars or whether you just see the near miss, it's going to be a really amazing sight. January the 1st.
That's Jonathan Nally, the editor of Australian Sky and Telescope magazine. And don't forget, if you're having trouble getting your copy of Australian Sky and Telescope magazine from your usual retailer because of the current lockdown and travel restrictions, you can always get a print or digital subscription and have the magazine delivered directly to your letterbox or inbox. Subscribing's easy. Just go to skyandtelescope.com.au. That's skyandtelescope.com.au, and you'll never be left in the dark again. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.